presentation. I'm going to talk about a very basic problem of Alice wanting to send a message to Bob. And the channel is a physical channel, so we expect it to be noisy. So there is noise in the channel, and there is a eavesdropper who is computationally powerful, maybe has a quantum computer or a powerful computer that can do a lot of computation. So the question is how Alice is going to send this message to Bob. So this message is a long-standing question in security, and we have many very clever solutions. And so most of them were ad hoc. Defining security was left for this particular setting, that there is an eavesdropping adversary. Was the work of, it starts with the work of Shannon. So he is the person who gives us the first attempt. So the first formulation of this in formulation of the problem, and the solution that he gives to this is a two-step solution. So the way Shannon solves the problem is, first he proposes, he introduces, invents information theory and shows how to do error correction, how to actually proposes that there is an error correcting code that you can use to have a error-free communication between Alice and Bob. So you should not worry about this noise in the channel, because we can have, if we use the right rate for communication, we can have a perfectly secure, perfectly reliable communication between Alice and Bob. So forget about this noise. And then the next step is to have establish a shared key. So give Alice and Bob a shared key, and then do a one-time pad. So have perfect security, perfect secrecy. So he introduces information theory. Now he uses it to define what perfect secrecy means, and proves that one-time pad gives you perfect secrecy. So this is a very nice, the very first formulation of security theoretically and proof of security that we have. So we know that one of the biggest challenges that this system has is that key is the same length as the message. So this makes this a very nice formulation and a very nice solution, but in practice it has limited use, because we have this challenge of establishing a long enough secret key. But what is also very interesting and less talked about is that this approach effectively isolates security from physical properties of the channel. So this is really what is, we take it for granted. In cryptography, we don't talk about it. So the whole development of cryptography has been on development of algorithms and around computation, and not thinking about physical channel, because physical channel, Shannon showed that we should not think about it. So we can have reliable communication, so let's forget about physical channel. And that's the way that cryptography has developed, so mostly actually. So, and in some sense it's nice, because we can actually have solved the problem in two steps, so reliability and security. So in some sense it's nice, but we're going to see it's not. It has also drawbacks. So going back to the same problem of eavesdropper looking at the channel, and the same problem of Alice wanting to send a message to Bob, 25 years later, after Shannon, Weiner gave a completely different solution. So now you have reliability and secrecy together. You do not do it in two steps. It's a one-step solution. There is no shared key, and instead you have a randomized encoder, which is called Wiretap encoder, and then there is a Wiretap decoder. So Weiner showed defined secrecy, again the same kind of information theoretic measure, but now asymptotically. And the requirement that asymptotically you have perfect secrecy. The bit for every bit, the leakage is going to go to 0. Reliability is same as Shannon. So, and nicely, very interestingly, he proved very cleverly, he proved that if this channel is noisier than the channel between Alice to Bob, then you can have perfect secrecy. So this is a very, again, very ingenious solution. Now, if you can see that, that we are not really using any secret key. So I think one of the first thing to notice is that in this solution, there is no shared key. There is no key required. Now, the stark difference to the previous one, here, security is tied to the physical property of the channel. So completely different now. So now you're saying that every time that you run this security system, if you design a wiretap code, every time that we want to run it in a different environment, we have to go back to the environment and see what are the properties of the channel, and then fine-tune the parameters of the system for that particular channel. So of course, no, it may look not good because in some sense we are in trouble, because now we have to estimate Eve's channel. So previously, so of course there are all these communication techniques we have that allows us to find noise in the receiver channel. So this channel, estimating this using communication techniques, is quite a feasible thing to do. But estimating Eve's channel noise is quite a different proposition, because now we have to know where the Eve is and what kind of antenna she's using and what kind of transceiver she has, and all that sort of thing, which makes it quite a challenging thing to think about. But what is very nice about this is that it actually gives us a kind of diversity in security. So now we are doing, for every environment, we are actually having a unique encryption system. Because now our encryption system really has to tie to the physical environment. And you can see that, that this is one of the nicest things that we can have. It can give you one of the biggest things that is talked about today is mass surveillance. And this actually contributes to better resistance against mass surveillance. Because now your adversary should be physically present in all the environment. And this is a very nice property that you can have. So I talk about this Wiener system because I think it has, of course, it has found a lot of application, but there are these nice properties that it has, and it actually think more about and use in a better way. So for this talk, I'm going to look at a particular wiretap code, which we call it hashed encode. It's a new construction. And I'm going to focus on finite length efficiency because, as I said, the traditional wiretap codes are asymptotic evaluation. So we look at finite length efficiency, and then we look at how we can use this system in a shared key setting, and some conclusion. OK, so just before going on to this to the wiretap code definition, I just to remind you, so one of the immediate applications of wiretap codes, and that's one of the reasons that we have this very big research in all engineering and computer science on wiretap code, is application to wireless communication. So every time that we have a wireless station, then an adversary who is further away gets a noisier version of this signal. Of course, we don't know the antenna of this adversary, so we don't know how much noise, but it is potentially that's the case that farther adversaries get noisier versions. So if you look at the near field communication, you can see that there are quite plausible cases that when you talk to your devices around you, and if you can assume that the adversary in this room, for example, is not going to have a huge antenna, then you can safely assume that you do have a communication with your receiver that is less noisier for the adversary. So I think that there are meaningful scenarios that you can think that this really fits the environment that we want to use. And of course, I think the other domain which is less talked about is this fiber communication. So in fiber tapping, you also introduce, if once the adversary taps a fiber, and this is a lot happens for fibers that are under ocean. So all of those, when you tap the fiber, you're introducing noise, and you can model it as a wiretap communication. So wiretap setting is a nice model, and it has application to many of the types of communication that we use today. Okay, so now let's to be able to say what this new construction is, just quickly go over some of these definitions. This is the definition of wiretap code. This is the encoder. As you can see, it's a randomized encoder, and there is a deterministic decoder. When you encode a message, it goes through this wiretap channel, so which noise is added to it. The main channel is also a noisy channel, so this receiver gets a noisy view. It decodes it. It can, because it has less noise, it can decode it. The adversary has a noisier channel, and it can see a noisy version of this. So these are the kind of definitions. So we need two things, reliability and security. For reliability is the traditional definition that received message should be the same as the sent one. And you average over distribution of the message. The security, this is the original definition of Wiener, that was rate of secrecy. And then later it was strengthened to be the total secrecy. So we want our uncertainty about the message after seeing for Eve, after having this Z, which is the view of the adversary, to be high. So this is for a 1-bit message. Then the strongest definition of security that we have is distinguishability security. This is cryptographic security, which is a statistical difference between sending two messages. So if we choose M0 or M1, any of them that is chosen, so if one of them is randomly chosen and sent, the view of the adversary should be almost the same statistically. So this is the definition that we are using. This is the definition that is introduced 3-4 years ago, and now by Bellare et al., and now it's used commonly. So efficiency of this system is for secrecy capacity. So secrecy capacity gives you the amount of information that you can send securely and reliably in every bit. So that's the secrecy capacity. So this is what we would like to have. For any channel, for any combination of noise, we can calculate this quantity. So for example, it becomes 0.1. So that's the secrecy capacity of this channel. And we would like for a code to achieve this secrecy capacity. That gives you the highest efficiency for the code. So if you look at the construction in this domain, there are two types. There are one that are designed for a specific error correcting code. Because remember that your main channel also has noise. So this class of construction, this is Mahdavi Farwardi, this is Rennes, and forgot the last one. So these are the people who designed wiretap code built into error correcting codes. Then there is a second class of construction that are modular construction. So we do some transformation for secrecy, and then we can use that transformation for any code which achieves any error correcting code. So sort of separating security coding and error correcting code. Of course, security analysis cannot be separated, but in terms of putting the two pieces together, you can separate them. So these are called seeded constructions. So it's Hayashi Matsumoto, Bellare Saravardi, and then Vardi Tyagi. So these are the existing construction of what is called seeded construction. Okay, so this is the new construction. This is seeded construction, to give you an example. So this is a modular construction. It's the seeded construction. And basically what the seeded construction means is that you have, remember that the encoding was a randomized encoder. So there are two pieces of randomness. One is randomness seed, which you randomly choose and send it over this reliable channel. And then there is this, for every encoding you have, so this is the message that you want to encode. You randomly choose a key. We call it a key, but this is not really a key. It's not a shared key. It's a randomness of encoding. As you can see, we are sending it as part of the code word. So this randomness is appended with this thing, which is application of this hash function on this and added to M. So effectively, our encoding is effectively application of a hash function to a random value and then added with the message and sent together with the key. So this is your error correcting code. So it can be, it has to be a capacity achieving, and then this is main channel, and then the receiver, you can do exactly the same thing. You have S, so you know the family of hash function which is used, so you apply, so because of error decoding, you can recover K. You apply HS of K and then this one, and then add it to remove this randomness. So effectively, this part is the randomness which is added to M. So that's basically the construction. So for a particular instantiation, that's what we have. So a particular instantiation, this family is effectively just a multiplication in a finite field. So all we have to do, we choose S and K. They come from two different, they can possibly be from two different fields, but we append enough zero to make them in the same field. And then all you have to do, you have to randomly choose K, multiply K and by S, add with M, and that's the encoder. Okay? So this is the encoding. So it's quite a simple encoding. So this S actually, so you can also get rid of this secure channel. This is the framework that we are going to talk about later. So really, we don't need this one. This is something that you can, S can be sent over the main channel, but because it can be used multiple times, it is amortized over a long message. So really, this is just for notation and just making it easy to explain. So this is the instantiation. You can see this is the message. This is the seed that we have chosen. This is the randomness of encoding. Possibly these two may not be of the same size. We append enough zeros. You multiply them using this in a finite field. You have this, you generated this pad. So XOR it with the message. The code that you have is, the first bit of encoding is this. This part appended with the randomness and then error correcting code. So that's what we said. So to prove security and optimality, we use a framework which is introduced by Belarete and Vardi into Crypto 2012. So they showed that they have, so effectively all we have to show is distinguishability security for uniform distribution, and that's what we do. And they showed that if you have this property, for this, under these conditions, you will have semantic security. So we use their theorem to show that because we can prove this property and our coding has this extra property, then we do have semantic security. And as I said, the seed is amortized over many applications of the channel. So effectively, what we can show is that each hash then encrypt construction provides semantic security, which is the strongest notion of security that we have, and it is capacity achieving. Okay, so that's the general construction, which we saw is very simple. Then the part that I like to show is now actually show that for this special type of scenario, that your main channel is noise-free. So in many applications, so in effect, we saw that the noise in the main channel is something that we have to remove it, because receiver has to have a reliable reception. So we have to do this extra error correcting code. But this extra error correcting code does not add to security. So to focus on the security property of the secure coding, we assume that this is noise-free. So just to make the way that secure coding works more clear. So if we assume that this is noise-free, then we can actually have a direct proof of security. So now what we have a wiretap channel, which is it's an adversary has a noisy view, but the main channel is noise-free. So whatever we send over the channel, receiver receives perfectly, but a noisy view is received by you can think about something is stored on a drive, which is noisy, and then when you read it back, then there is some noise in this. So if we now look at what we had, so this was the construction that we described before. So now when there is no extra error correcting code that makes the system more complex than it needs to be. So we have this one. When it goes through the adversary's channel, then there is some noise is added here, some noise, independent noise, because noise in different parts of the channel are independent. So the two noise are added here. And if you look at what we obtain what the view of the adversary is, because this is the part that the adversary is interested. This is the message part. So message is, in fact, is added with the HS of K, which we had added to it. But now part of this K is revealed because of this, because we sent this key. So this is conditioned over this. And then this new N1 is added to this whole thing. So this is the view of the adversary. And if you look at this one, this is, in fact, what we prove is that this is a two-source extractor. And so effectively, this thing that we have here is a random pad that masks this message. So effectively, what we are in this direct security proof that we have, we can show that the effect of doing this and the noise of the channel is that we have a two-source extractor that extracts from the noise in the channel and the randomness that we introduce in the coding. So I guess we can skip this one. So we can actually show that. So this is comparison of our system and the system that is the comparable system. This is the BTV system. And if we look at the two, you will see that the rate of these two, so the effective rate. So I think the point that I'd like to say here is that effective rate means that so all the evaluation of one-time wiretap code is in or asymptotic evaluations. So in practice, we want to send it for one message. So if I want to talk to a pacemaker, for example, so then it is a one-time communication. So we have to send the seed also. So what we are sending, the effective rate is the length of the message divided by the length of the code word and the seed. So if we calculate these two effective rates for the two cases, for these two two construction, we will see that this one is going to have a better effective rate in all cases once you go beyond certain message length. So these are the examples. This is 32-bit semantic security. So this is 64-bit semantic security. And you can see this red line, which is the H then encode system has a better performance. I think the last thing that I like to say here is, which I think makes this construction nice, is that now let's think about this setting. So we have our wiretap code, wiretap channel with a noise-free main. So the channel to the receiver is noise-free. Eve is outside, so she is going to get a noisy view of communication. And we are allowing to have a secret key. So we do allow encoder to have a shared key. So we want to see what can we gain. So if we use one-time paths, so of course we can share a key, and then we can use the same length. So the key is the same length as the message, and we construct the ciphertext, we send it, and the adversary who sees even a noisier view of this one, she won't see anything. She won't be able to understand anything. The nice thing about hash then encode construction is that it allows you to reduce the length of the key. So effectively, by doing this, and the way that I showed you, that effectively this construction extracts from the noise of the channel and the randomness of encoding. So this translates to reducing the length of the key that you need to have for this secure communication. So here you can see that the reduction in this length of the key is B is the length of the message. This is the mean entropy of the channel noise, and this is the semantic security. The level sigma is the number of bits of semantic security that you need you have required for this. So this can become much smaller than this one. I should say that this construction that we have has appeared in other domains. So this adding HS of K to the message has appeared first in the context of entropic security by Dodis and Smith in 2005, and then later also by Bellari in XTX, but in different contexts. So this is the way that we have. So that's all I wanted to say. So to conclude, I guess one of the main points that I thought is very important to raise is that physical properties of environment is an important resource for adding security and really making security specialized to environment and make the life of a mass surveillance attacker much harder, because you're adding a second factor, and we did not have this second factor. All the factors that we have are information. So that's quite a nice thing to use. So we need a lot more formal studies in this domain. So H2 hashed encode can be used without a shared key, which gives you efficient finite length construction. If it's used with shared key, you can shorten the length of one-time path. And finally, it looks that you should be able to use, if you choose your parameters correctly, you should be able to have perpetual one-time path using the noise in the channel only. So you start with one key, and then you use the noise of the channel to continue the communication. So with that, and these are my students and postdocs who have helped me. We work together, and these are the results of the work. Thank you.